So in continuous manner, next topic we are going to discuss the hysteresis. We know that ferromagnetic materials exhibits a phenomenon that is called hysteresis. Already I told that. Hysteresis is a phenomenon in which the two physical quantities are related in a manner. One of the quantity either decreases or increases with respect to the other one. That phenomenon is known as hysteresis. So this hysteresis phenomenon is explained with the magnetization and applied magnetic field. That is simply called B.H. loop. The lagging of magnetization behind the applied magnetic field is called B.H. loop or B.H. curve. So for that, let us take a ferromagnetic material is placed in the magnetic field. When the ferromagnetic material is placed in the magnetic field, the magnetization is developed in the ferromagnetic material with increasing field along the x-axis. The magnetization is also increases and it attains a maximum value that is called saturation magnetization. So the hysteresis phenomenon can be explained with the B.H. loop or B.H. curve. So the applied magnetic field takes along the x-axis and magnetization takes along y-axis. We plot a graph or loop or a curve. This is called B.H. curve. Or B.H. curve or loop is defined as the lagging of B value behind applied magnetic field is called B.H. loop or B.H. curve. So for that, let us take a ferromagnetic material. The ferromagnetic material is placed in the magnetic field. The magnetization is developed or established in that ferromagnetic material up to maximum value. This maximum magnetization is called saturation magnetization. Beyond this magnetic field, with increasing magnetic field, the magnetization does not increases. So that the applied magnetic field reverts to zero. The magnetization does not retrace to zero and it follows a new path from A to B. So even the applied magnetic field H becomes zero, some magnetization is left in the ferromagnetic material, that is called residual magnetization or retentivity. In this graph, the retentivity is equal to OB. OA is equal to saturation magnetization, that is maximum, and OB is equal to retentivity or residual magnetization. The residual magnetization is observed when the applied magnetic field reverts to zero, some magnetization is left in the specimen, that is called residual magnetization. Next, the applied magnetic field increases in negative sign. The magnetization gradually decreases and it becomes zero at point C in the graph. That is residual magnetization. Coercivity. If the applied magnetic field reverses to zero, reverses to negative value, the magnetization becomes zero at point C. This is called coercivity. The required field is called coercive field. The coercivity in the graph is equal to OC. Again, the applied magnetic field increases in negative sign. The magnetization is slowly decreases in negative sign and it attains a maximum value in the negative sign is also. This is saturation magnetization in negative magnetic field. This is the half of loop from 0 to A to B, B to C, C to D. And next, the remaining half loop is also closed by increasing the magnetic field from negative to 0, 0 to positive. The remaining loop is closed. So the formation of this loop or B.H. curve indicates how much of energy is lost in one complete cycle that can be calculated with the hysteresis loop. So hysteresis is a phenomenon in which the two quantities are related in a manner. One of the quantity, that is B value, either increases or decreases with respect to the applied magnetic field. So that is the B.H., that is the hysteresis loop. This hysteresis loop can be observed with the BH curve or BH loop. So the lagging of B value behind H is called BH loop or BH curve. The magnetic flux density increases non-linearly and reaches a saturation position at point A. The magnetic flux density remains constant in a specimen in the absence of electrical field is called reminiscence or residual magnetization. The coercivity means the magnetization becomes zero in the negative magnetic field is called coercivity. So based on the formation of the BH loop or BH curve, the magnetic materials are the magnetic materials are classified into two types: hard magnetic materials and soft magnetic materials. So hard magnetic materials, soft magnetic materials or hard magnetic materials can be classified, is classified based on the formation of the hysteresis loop or BH curve. So that is soft magnetic materials means in the soft magnetic materials the hysteresis loss is very less. The formation of the curve is in small size. Such magnetic materials are known as soft magnetic materials. The examples of the soft magnetic materials are iron, nickel, cobalt, all cuneiform and cuneiform. So coming to the properties of these soft magnetic materials. So the soft magnetic materials are heated to the required temperature and cooled slowly then and to prepare the soft magnetic materials. They can easily magnetize and demagnetize. Their hysteresis loop is very less. The area of hysteresis loop is small and hysteresis loss is small. They have high magnetic susceptibility and permeability. They exhibit low retentivity and coercivity. They exhibit high resistivity. They require a low magnetic field to magnetize. So these soft magnetic materials are used to prepare the magnetic core materials. These magnetic core materials can be used in the transformers, electrical motors and the magnetic amplifiers. This is the soft magnetic material. The magnetic materials which have the less loss of hysteresis is called soft magnetic materials. And other one is the examples are iron, silicon alloys, nickel iron alloys, iron cobalt alloys. So the applications of the soft magnetic materials, they are used in the electrical equipments and magnetic core of transformers. They are used in the motors and the sensors. They are used in the microwave isolators. And hard magnetic materials, the magnetic materials which have the high hysteresis loss, such materials are known as hard magnetic materials. In these hard magnetic materials, the forming BH loop area is very high. The magnetic materials are heated to required temperature and suddenly cool down by dipping into the cooled solution to prepare a hard magnetic materials. So the hard magnetic materials are not magnetized and demagnetized easily. Their hysteresis loop is abroad. The area of hysteresis loop is large and hence the hysteresis loss is large. They have low magnetic susceptibility and permeability. They exhibit retentivity, high retentivity and coercivity. They exhibit low resistivity. They require high magnetic field to magnetize. The examples of the hard magnetic materials are cobalt steel alloys, carbon steel alloys, tungsten steel alloys, chromium steel alloys. The applications of these hard magnetic materials, these materials are used to prepare permanent magnets. They are used these permanent magnets are used in the loudspeakers and detectors. The hard magnetic materials are used in the speed demasters and sensors in the automobiles and motors. They are used in the DC meters and measuring devices. This is the classification of the magnetic materials based on the formation of the hysteresis loop or pH curve.